Hey everyone, let's explore the time complexity of two popular search algorithms in Java, linear search and binary search. Understanding the time complexity of these algorithms is crucial for making informed decisions about which one to use in different scenarios. Now, let's get started. The linear search is simple, works on unsorted data, but less efficient for large data sets. Let's see this example where we have an unsorted list of elements. We want to search for the key element 16. The linear search starts scanning the list from left by checking each element one by one until it finds the key element or reaches the end of the list. Here, there are 9 comparisons to get the target key element. Here, the best case would be when we search for a key element that is present at the first index. And the best case time for a list of n elements would be big O((1), which is constant and can also be written as omega or theta of 1. On the other hand, the worst case would be when we search for a key element that is present at the last index. And the worst case time is then big O((n). For the average case, you need to find out all possible cases and the time taken in each possible case, and then divide it by the number of cases. So this kind of analysis is very difficult and may not be possible for every algorithm. Mostly the time we get for average cases will be similar to worst case, so that's why we prefer finding the worst case time of an algorithm. For example, you need to find the time in case we are searching for a key at the first index, then at the second index, then third, and so on. So the time complexity will also be big O((n). And of course, we can use any of those notations. Here is a simple code written in Java that demonstrates the linear search algorithm. You can also find the link for the GitHub repository in the description below. Here we have the linear search method that performs the linear search by iterating over an array one by one until it finds the key element. Now let's explore binary search. Let's understand it by taking the same example. And here we are also searching for the key element 16. First thing is that binary search works on sorted lists or arrays. It follows divide and conquer strategy, which divides a problem into subproblems to obtain their solutions. And after that, it combines these solutions to get a solution for the main problem. Now, binary search repeatedly divides the search space in half by comparing the target value to the middle element. If the target is not found, it eliminates the half of the remaining elements in each iteration. For this, we need 2 index pointers, left and right. The elements can also be organized in a high balance tree in a way that for every node, all elements that are smaller will locate on the left side, and the greater will locate on the right side. Now let's see how it divides the search space. First, it starts with the pointers at the very left and right sides of the list. In this case, the middle index will be 5. Now, since the element in index 5 is not the key element we are searching for, it checks if the key is greater than that value. And if it is, then it repeats the same process on the right half of the list or the tree. If the key is less than the value of the middle index, then it searches in the left half of the list or the tree. In our case, we have the key 16 and the middle is 8, so it searches farther in the right side. And now the left index has been increased to be greater by 1 than the middle index, and the right index still the same. So the new middle index is 8, which has the element 16. And this is the key element we are searching for. What if the element doesn't exist? If we are searching for the element 15, for example. The algorithm starts with the initial indices, with middle index 5, and it continues with the right half of the list. The key element is still not found and is less than the element in the middle, so it eliminates the search space to the left side of the middle, meaning it decreases the right index by less than the middle index by 1. And now the new middle index is 6, with its element 9 that is less than our key. So it goes to the right side of the middle index. The middle index 7 with its element 12 still less than our key element. So the left index is now greater by 1 than the middle index, and the process stops since now the left index became greater than the right index. So the element couldn't be found and it doesn't exist. Now, what is the time complexity for this algorithm? The same with the best case, that will be if our target element is the root element of the tree. So the best case time will be big O 1. The worst case would be if we are searching for a leaf element or if the element doesn't exist. And this depends on the height of the tree or the size of our list. The height of a high-balanced binary search tree is log of n. So the worst case time is log of n, and n is the number of elements in our list, and represents the maximum number of comparisons that the algorithm performs until it finds the element. So if our list contains 16 elements, then the maximum number of comparisons will be 4. We can also represent the binary search algorithm within this simple code in Java, where we have the binary search method that performs the binary search on an array by iterating over it as long as the left index is less equal to the right index, and it divides the search space until it finds the element, or it breaks when the left index exceeds the right one, which means that the element doesn't exist. Well, that's it for today's video. I hope it has been informative. Please don't forget to like this video if you found it helpful. Subscribe for more content and hit the notification bell to stay updated. Thanks for watching.